Okay, this is a solution to part B of number 3. Um, part A is uh, um, an inelastic, sorry, a plastic or an inelastic collision where they stick together. That's the easier one mathematically. Um, part B is elastic, they bounce apart, so we have to go through that. All right, so what's happening is you have a train car with a mass of 2,500 kilograms. Mass is 2,500. And it has a speed of 21 meters per second. Let's say it's going this way. And then it collides, excuse me, with another train car that's initially at rest. The second train car has a mass of 3,000 kilograms. Okay, this is at rest. And so part B says if they bounce apart, so we're going to assume that it's an elastic collision. What are the velocities after the collision? Okay, well, the first thing we're going to do is conservation of linear momentum. What we're going to see, I've mentioned this before, is that that's not enough information for us to figure out what's happening after the collision. And so we're going to have to come up with something else. And that something else is we're going to say, if you add up all the kinetic energies of the system before the collision, it's equal to all the kinetic energies of everything in the system after the collision. So no energy is lost. Okay, that's so what's happening is they're smashing into each other, they're deforming, and it takes energy to cause that deformation, and then they spring back, and that puts all the energy back into the things. There's no energy lost in the deformation anymore. That's sort of a description in words of what's happening in an elastic collision. Um, All right, so first let's do conservation of linear momentum. So I'm going to choose a coordinate system with the x-axis this way, y-axis that way, although that's not going to come into it. Everything's happening along the x-axis. So I'm just going to do the x components. But remember, these are components of vectors, so there is positive and negative. Okay, so before the collision, we have a mass of 2,500. And a velocity of 21 in the positive x direction. So that's a positive 21 plus a mass of 3,000 times a velocity of 0 because it's at rest. And after the collision, the masses don't change. So we still have the 2,500. And that has some velocity v1. And the second one has some velocity v2. Okay, so 2,500 times 21 is 52,500. Is equal to 2,500 V1 plus 3,000 V2. I think, so what we're going to do is we're going to come up with two equations and we're going to solve this system of two equations for two variables. So we might as well simplify stuff. Let me divide everything by 2,500. So we get 21 is equal to V1 plus 6/5 1.2 V2. Okay, that's our first equation. So I'll set that aside. And now we'll go on to the one that says the kinetic energies are are the same before and after. So you can think of this as the total kinetic energy of the system and it's unchanged by the collision. Okay, so all we have to do is add up the kinetic energies before, add them up after, and set them equal. So before the collision, kinetic energy is 1/2 times the mass times the speed squared of the first one plus 1/2 times the mass of the second one times its speed squared before the collision. And that's equal to 1/2 of 2500 V1 squared plus 1/2 of 3000 V2 squared. Okay, and I'm going to simplify this. Let's see, I can divide everything by, well, get rid of the halves, divide everything by 1/2, and then I'm going to divide everything by 2500. So we have 441 is equal to V1 squared plus, that's 1.2 V2 squared. And there's our second equation. And at this point, all the physics is done, even, I guess, even before I started simplifying things. We're done with all the physics. All we have to do is come up with a system to this solution to this system of equations. But it's, that's not to say it's not tedious. If you get to this point on a problem, I give you 80% of the points, but it's nice to get all the points. So what do we have to do? Well, what we're going to do is, in the second equation, 2 star, V1 only appears squared. So I'm going to use equation 1 star, come up with an expression for V1 squared, and then I'm going to plug that into the second one. So that first star equation, it says, if I rearrange it, V1 is equal to 21 minus 1.2 V2. And so if I square both sides, we get V1 squared. And the second side, we get 441. I'm just foiling this, minus okay, stay with me. 21 times 1.2 times 2, 50.4. That's V2. And then plus 1.44 V2 squared. And now we can substitute that into equation 2 star. So we get 441 is equal to, now I'm substituting this right-hand side of the equation for V1 squared. So we have 441 minus 50.4 V2 plus 1.44 V2 squared. That's V1, all the stuff in parentheses, and then we also have to add on the 1.2 2v2 squared. The 441s cancel out, which I guess is always what's going to happen in the case where one of these two objects is at rest before the collision. And so what we have is the equation 0 is equal to negative 50.4 V2 plus 2.64 V2 squared. And this one, any of these where you start with one of the bodies at rest, you can just solve it by factoring, otherwise use the quadratic formula. You should not ever be using the quadratic formula by hand anymore. It just, your calculator does it somehow. So figure out how to do it in your calculator, or you can always just Google it on your phone. Just Google quadratic formula calculator or whatever and plug in the numbers. But so what we have here is factor out V2, and you get 2.64 V2 minus 50.4. And so the solutions to V2 are 0, or the other solution is 50.4 divided by 2.64, so 19.09. Okay, so which of these is the solution we want? We know that only one thing happens, so which one of these happens? Well, what you're always going to get is one of the two answers that comes out of this solution represents what was going on before the collision, and the other one is the one that we want. So if you look back, the one that I called car 2 was the one that was at rest before the collision, and so this one we're going to throw out. That was what was going on before the collision, and that means this is the one we want. Okay, so V2, these all represent x components of velocities, so you can think of this vector as 19.09, 0. We also want to know what's happening with V1, but to do that, you just have to plug it back into every equation you have up above, if you've done things right, is correct. And so you can use that, whatever's easiest to find V1. So 21 minus 1.2 times 19.09. V1's velocity then is negative 1.908. So the velocity vector of the car that I drew on the left is negative 1.91, I'll call it 0. So that's how to do a calculation involving an elastic collision. Those are the more tedious ones. The inelastic collisions are a little simpler mathematically. Still, make sure that you understand that the physics of it was pretty simple. We just used two things, came up with two equations. The tedious part then is just using those two equations to solve for the values. Okay, so that's the solution to part B of conservation of linear momentum number 3.